So, we have been talking about the Hamel basis and basis. Now, again I emphasize that when you study Hilbert spaces or Banach spaces, the idea of basis of linear algebra is not of much use. In linear algebra, a subset B is said to be a basis if it is linearly independent and the linear span is the whole vector space. This is called Hamel basis in functional analysis. In Hilbert space theory, whenever we are talking about Hilbert spaces, if we are talking about this, this will be qualified and will be called Hamel basis. So, in short, a basis in the sense of linear algebra means Hamel basis. When I suppress the word Hamel and I just say basis, it means something very different. Okay, so a basis in a Hilbert space is first of all a linearly independent subset B, and then you take the linear span of B and take its closure, and you are supposed to get the whole space. Such a set is called a basis. Alright. Now, why is it that a Hamel basis is not very useful in Hilbert space theory? Now, the number of elements in a Hamel basis is going to be pretty huge. If we have a Hilbert space which is not finite dimensional, then the Hamel basis will be very, very large. It cannot be countable. Infinite dimensional Hilbert space cannot have a countable Hamel basis. The number of elements in a Hamel basis will be very large. Of course, if the space is finite dimensional, then there is no distinction between basis and Hamel basis. So, for finite dimensional vector spaces, there is no problem. Whether you call it Hamel basis or whether you call it basis, it is the same concept. Now, why is it that Hamel basis is not particularly useful? Hamel bases are huge entities. The cardinality of a Hamel basis is uncountable. A Hamel basis will have too many elements. It will have as many elements as there are real numbers. The cardinality, in short, is the cardinality of the continuum. This is not going to be used by us, and therefore we shall not give a detailed proof of this. What I will do is, in this single slide, I will give you a sketch of the main points involved in the proof. So, this can be seen as follows. Now, first of all, a finite dimensional subspace of a Hilbert space is closed. That is an easy exercise. Take a Hilbert space H, take a finite dimensional subspace. Show that a finite dimensional subspace is closed. Closed in the sense of metric spaces. Every sequence, every convergent sequence will have its limit in the space itself. So, if V is a finite dimensional subspace of a Hilbert space H, and if Xn is a sequence in V converging to P, then the limit is also in V. That is not difficult, and I leave it as an exercise. Now, if you have a infinite dimensional Hilbert space and you take a finite dimensional subspace, if you take a finite dimensional subspace, then it is closed and it has got empty interior. So, every finite dimensional subspace of an infinite dimensional Hilbert space is a closed subspace with empty interior. Now, suppose a Hamel basis is countable. Suppose we have got a countable Hamel basis V1, V2, V3, etc. Then let us do the following. Let us take the first n vectors V1, V2, etc., Vn, and take its linear span, and let us call this linear span En. So, what do we know about En? It is finite dimensional. What is the ambient space? Infinite dimensional. So, En will have empty interior and it will be closed. Now, let us take the union of all these Ens. We want to show that the union of all these Ens is H. How do you show this? Let X belongs to H. Let X belongs to H. Then, since V1, V2, V3, etc. is a Hamel basis, X will be equal to lambda 1 V1 plus lambda 2 V2 plus etc. plus lambda n Vn for some scalars lambda 1, lambda 2, lambda n. In other words, x must be in En for some n. So, H must be the union of all the Ens n going from 1 to infinity. So, we have expressed H as a countable union of closed sets, each of which has empty interior, and H is a complete metric space. We have obtained a contradiction because the Bayer category theorem, recall, says that if X is a complete metric space, you cannot write X as a countable union of closed sets, each of which having empty interior. That is not possible, and so we obtained a contradiction. So, this is how you see that an infinite dimensional Hilbert space or an infinite dimensional Banach space cannot have a countable Hamel basis. Hamel basis will be uncountable, it will have too many elements. So, our definition of a basis, a more practical definition of a basis, is a linearly independent set with the property that the closure of the linear span will be the whole space. Closure in the sense of metric spaces, metric topology. So, now let us look at a number of examples of basis in Hilbert spaces. So, let us take our favorite examples of Hilbert spaces and let us write down basis in these Hilbert spaces. The classic example of a Hilbert space is L2 of AB, closed interval AB. And since we are discussing Fourier series, we would take A to be minus pi and B to be pi. So, we are looking at L2 of minus pi pi. Now, we know that the partial sums of a Fourier series of f, which is in L2. So, what does the Parcel formula tell you? The Parcel theorem says that if I take the partial sums converge to f in L2 norm. We have seen this in the second module in this course. So, SNF, the nth partial sum of f, SNF converges to f in L2, which means that the finite linear combinations of 1 cos x, sin x, cos 2x, sin 2x, etc. are dense in L2, because after all SNF is a finite linear combination of 1 cos x, sin x, cos 2x, sin 2x, etc. So, if I take the linear span of 1 cos x, sin x, cos 2x, sin 2x, etc., this linear span will contain the partial sums of all the elements in L2, and so its closure of this linear span will be the whole of L2. That completes the argument for L2 of minus pi pi. We have exhibited a basis. Classical Fourier series gives us an example of a basis. Let us take another example. Take L2 of minus 1 1. Take L2 of minus 1 1. We know that polynomials are dense in C of minus 1 1 in sup norm. That is a Weierstrass approximation theorem. The Weierstrass approximation theorem says that polynomials are dense in C of minus 1 1 with respect to sup norm. But convergence in sup norm implies convergence in L2 norm. We have used this fact frequently in the previous modules, and so I will not explain why this is so. We have used this fact, and there I explained to you convergence in sup norm implies convergence in L2. If Fn converges to F in sup norm, means Fn converges to F uniformly. If Fn converges to F uniformly, then Fn will converge to F in L2 norm. It will converge also in L1 norm. It will converge in LP norm for every P. Okay. So, now since polynomials are dense in sup norm, polynomials are also dense in L2 norm. Now, Lusin's theorem says that C of minus 1 1 is dense in L2 with respect to the L2 norm. So, polynomials are dense in minus 1 1. Set of all polynomials is dense in minus 1 1. So, polynomials are obtained by taking finite linear combinations of 1 x, x squared, x cube, etc. So, now if you look at the sequence 1 x, x squared, x cube, etc., and if I take the linear span, then its closure will be L2 of minus 1, 1. Okay. So, now where do we go from there? We have this list 1x, x squared, etc. And we know that the linear span is dense in L2 of minus 1, 1. But what we are interested in a orthonormal basis. After all, L2 is a Hilbert space. It's a vector space with an inner product. So, we are not only interested in a basis like 1x, x squared, x cube, etc. We are interested in an orthonormal basis. So, how do I go from a basis to an orthonormal basis? Recall the Gram-Schmidt's process from elementary linear algebra. So, I could take 1x, x squared, x cube. I could subject this sequence 1x, x squared, x cube, etc. to the Gram-Schmidt's process. I will produce P0x, P1x, P2x squared, etc. These P0, P1, P2 are orthogonal system of vectors, and linear span of 1x, x squared, x cube, x to the power n is the same as the linear span of P0, P1, P2, etc. up to Pn. That's also a part of the Gram-Schmidt's process. It's a byproduct of the Gram-Schmidt's method. So, since the linear span of 1x, x squared, etc. is dense in L2, linear span of P0, P1, P2, etc. is also dense in L2, and since P0, P1, P2, etc. is orthogonal, they are linearly independent. So, I would have produced a orthogonal or an orthonormal basis for L2 of minus 1, 1. The question is, if I subject 1x, x squared, etc. to the Gram-Schmidt's process, what comes out? I had denoted it by P0, P1, P2, etc. But what are they explicitly? No prizes for guessing. The very symbol Pjx should give you a hint that the resulting polynomials are Legendre polynomials. So, we get the sequence of Legendre polynomials as the orthonormal basis for L2 of minus 1, 1. As an exercise, you must prove this using the fundamental orthogonality lemma which we established in module 5. You must go back to module 5 and you must recall this fundamental orthogonality lemma. We are going to use it again very soon. So, that is the importance of Legendre polynomials. Now, let us other examples. The next example is that of Hermit functions. We already encountered Hermit functions earlier in this course when we did the Fourier transforms. So, we shall come back to this again. So, let us recall the Hermit polynomials. The Hermit polynomials are solutions of the Hermit's differential equation. What is the Hermit's differential equation? Y double prime minus 2xy prime plus 2 lambda y equal to 0. Now, you can look for a power series solution of this Hermit's differential equation. So, that is display 7.3. Let us look for a solution y equal to summation n from 0 to infinity a n x to the power n. Let us substitute this into the differential equation. So, you must compute y double prime. What is y double prime? Y double prime will be summation n from 0 to infinity n plus 2 into n plus 1 into a n plus 2 x to the power n. We have seen this when we did the Legendre's equation. The same thing you should imitate. You should go exactly as you did for the Legendre case, and your y double prime will be n plus 2 into n plus 1 a n plus 2 x to the power n. Then the minus 2xy prime, you differentiate with respect to x and you multiply with respect to x. So, that is degree preserving. So, minus 2xy prime will be summation n from 0 to infinity minus 2 n a n x to the power n. Finally, you got a 2 lambda y, which is straight away summation n from 0 to infinity 2 lambda a n x to the power n. Put them all together and you get the last displayed equation in this slide. Summation n from 0 to infinity, the x to the power n is common, all the terms have x to the power n, all summations go from 0 to infinity. And then what is the coefficient of x to the power n? A n plus 2 into n plus 2 into n plus 1 minus 2n a n plus 2 lambda a n equal to 0. This power series must be identically 0. And when is a power series identically 0? When all the coefficients are equal to 0. So we must equate all the coefficients in the last display in this slide, and we'll get the recursion formula for the successive coefficients of the Hermite's equation. So let us write down this recursion formula. An plus 2 will be 2 times lambda minus n upon n plus 1 into n plus 2. So substitute n equal to 0, 1, 2, 3. So when you put n equal to 0, we get a2 in terms of an. An plus 2 is what? An plus 2 is 2 times lambda minus n an upon n plus 1 into n plus 2. So when you put n equal to 0, you get a2 in terms of a0. When you put n equal to 2, you get a4 in terms of a2, but a2 is expressed in terms of a0. So all the even ones, a4, a6, a8, etc., will all be expressed in terms of a0. The odd ones, a3, a5, a7, will all be expressed in terms of a1. And you do the algebra. Requires a little patience to write out all the terms, but you do it, it's easy. You get y of x equal to a0 times brace bracket 1 plus 2 lambda upon 2 factorial x squared plus 2 squared lambda into lambda minus 2 upon 4 factorial x to the power 4 plus etc. plus a1 into braces x plus 2 times lambda minus 1 upon 3 factorial x cube plus 2 squared times lambda minus 1 into lambda minus 3 upon 5 factorial x to the power 5 plus etc. Now, a strange thing happens. If lambda is say 2, for example, then look at the first power series, a0 times the power series. Look at the coefficient of a0. Look at the term involving a0. That truncates to a polynomial of degree 2. If lambda equal to 4, that will truncate to a polynomial of degree 4, etc. If lambda equal to 1, then the term involving a1 will truncate to a polynomial of degree 1. If lambda equal to 3, it will truncate to a polynomial of degree 3, etc. So what do we conclude? We conclude that if lambda is an integer, non-negative integer, then the differential equation admits a polynomial solution. The differential equation admits a polynomial solution, so we get polynomial solutions. Can the differential equation have two linearly independent polynomial solutions? Let us go back to the differential equation. What is the Wronskian of two solutions? The Wronskian of the two solutions will decay to 0 as x goes to infinity. So look at the Wronskian of two solutions and look at the behavior of the Wronskian as x goes to infinity, and you can conclude that you cannot have two polynomial solutions which are linearly independent. Of course, here in this specific differential equation, directly also you can argue. You can say that the general solution has been displayed here, and obviously when lambda is an integer, you can only have one polynomial solution. The other series doesn't truncate. That's the more elementary way of looking at it. So either of the two ways you can use, and you can conclude that whenever lambda is a non-negative integer, there is one up to scalar multiples polynomial solution. These polynomial solutions are called the Hermit polynomials. Let us denote them by f lambda of x when lambda is a non-negative integer. So we got these Hermit polynomials, and let us prove that these Hermit polynomials are orthogonal in a certain sense. So unlike the case of Legendre polynomials, there is no universally accepted convention for normalizing these polynomials. Remember that when we discussed the Legendre polynomials, we made the convention that Pn of 1 is 1. So that's how we fixed the arbitrary constant and we normalized the Legendre polynomials. For the Hermit polynomials, there is no universally accepted normalization condition. So Hermit polynomials are orthogonal. In what sense are they orthogonal? That's theorem 60 on the slide. The polynomials f lambda of x, where lambda runs from 0, 1, 2, 3, etc., forms an orthogonal family in the following sense: integral over r fmx fnx e to the power minus x squared dx is 0 if m is not equal to n. Remember that fmx is a polynomial, fnx is a polynomial, and e to the power minus x squared decays very rapidly at plus infinity and minus infinity. In fact, e to the power minus x squared is in the Schwarz class, remember? And when I multiply e to the power minus x squared by polynomial, it is again in the Schwarz class. It again decays very rapidly. So the integral makes perfect sense. And the integral is actually going to be 0 if m and n are distinct non-negative integers. Now what happens is that we look at this integral and we look at this e to the power minus x squared and we split it and we give part of it to fm and part of it to fn. So we define hnx, little hnx equal to fnx into e to the power minus x squared by 2. And these functions hnx are called Hermit functions, and what the integral says is these Hermit functions are orthogonal functions with respect to L2 of R, namely integral over R hnx hmx dx is 0. The e to the power minus x squared has been split into a product of two things, e to the power minus x squared by 2 into e to the power minus x squared by 2. One e to the power minus x squared by 2 has gone with fm and it becomes hm. The other one goes with fn and it has become hn. And we got the orthogonality of these Hermit functions in the space L2 of R. Let us dispose of this orthogonality result quickly. So we take the Hermit's differential equation, y double prime minus 2xy prime plus 2 lambda y equal to 0. Now this Hermit's differential equation can be converted into self-adjoint form. How do I convert it into self-adjoint form? Look at the first two terms in the differential equation, try to make it an exact derivative. How will you make it an exact derivative? The obvious way is to multiply the differential equation by e to the power minus x squared. The exponential function is never 0, so we are not introducing any spurious singularities. It's a reversible process. I can multiply the differential equation by e to the power minus x squared. The first two terms will combine to become an exact derivative, namely ddx of e to the power minus x squared y prime. And so the self-adjoint form is displayed. Now we know that when lambda equal to m, we have the solution fm. When lambda equal to n, we have got the solution fn. And so we got the two last displayed equations in the slide, ddx of e to the power minus x squared fm prime plus 2m fm e to the power minus x squared is 0, and ddx of e to the power minus x squared fn prime plus 2n fn e to the power minus x squared is 0. What do we do next? We multiply the first by fn, second by fm, integrate by parts and subtract. We have done this exercise for the Legendre polynomials. We repeat the same idea with Hermit polynomials. So when we do this, we will get the orthogonality of the polynomials fn and fm with respect to the weight function e to the power minus x squared. In other words, we will get this integral equation, integral fmx fnx e to the power minus x squared dx is 0 when m is not equal to n. Now this is fine, but what we are interested in a closed form expression for these polynomials fn. Now you again go back to Legendre polynomials and recall that in the case of Legendre polynomials, we derived the Rodrigues formula. What did the Rodrigues formula say for Legendre polynomials? Pnx equals 1 upon 2 to the power n n factorial nth derivative of x squared minus 1 to the power n. We want an analog of the Rodrigues formula for Hermit polynomials. We will do that next.